learners, my name is Zanele Saleni from Ebenezer Madomboze High School. Welcome to ECDOE Broadcast Studio. Today's lesson is about the overview of Paper 2. Paper 2 is composed of different topics. There are organic molecules, there is energy and change, rate and extent of chemical reactions, dynamic chemical equilibrium, acids and bases, and redox reaction. So those are the topics that paper 2 covers. If you look at your paper 2 in terms of marks, matter and material is 58 marks. And if you look at chemical change, it's 92 marks. You are writing a paper that is out of 150, and that paper has got a duration of 3 hours. When you get into an examination, you'll find that you have got different question numbers. Question 1 will always be your multiple choice question. And if you get into a multiple choice question, you have got 10 multiple choice questions. Each question, it is 2 marks. It's very important that you score each and every 2 marks, because you lose 2 marks, that means you have got 18 out of 20. Now, when you are looking at the multiple choice questions, a learner should have understanding on concepts. You should have understanding on principles. You should have understanding on laws, the relationship between variables. And when we talk of variables, we talk of the independent variables, we talk of the dependent variables, we talk of the controlled or the constant variables. So learners are always encouraged to make use of the formula sheet, because sometimes the formula sheet gives summary to laws and principles that we get to talk about in physical sciences. In the multiple choice question 1, it tests learners' understanding in concepts. It tests learners' understanding in the principles that the physical sciences talks to, the laws, and it talks to the different variables that learners were taught, your dependent, independent variable, and the constant variable. So learners at all times, they should make use of the formula sheet. It gives summary of laws as well as the relationship between variables. Now, the use of multiple choice question, it addresses all key aspects and key concepts chemistry is outlining from the examination guideline. Now, the first 3 questions after the multiple choice, question 2, question 3, and question 4, are out of 58 marks. And all of those questions are from organic chemistry. Question 2 is looking at nomenclature and structures. Question 3 is looking at organic properties of your physical properties of organic molecules. And the last question on organic chemistry is looking at inorganic reactions. Round about 58 marks, which is 38.7% of the paper. Now, let's get into organic chemistry. Now, in organic chemistry, a learner needs to know hydrocarbons. That's number 1. Number two, a learner should be able to differentiate all other homologous series. And in order for a learner to be able to differentiate all homologous series, a learner should know the functional group of each and every homologous series. Now, we are talking of your alkanes, your alkenes, your alkynes, your haloalkanes, aldehyde, ketone, esters, alcohol, and carboxylic acid. Now, from writing the general formula and the functional group, from writing the general formula and the functional group, learners should be able to draw the structural formula for each and every organic compound that is taught. A learner should be able to give an IUPAC name for each and every organic compound that has been taught in class. Now, when a learner is writing organic names or your IUPAC names for organic compounds, there are 7 steps that a learner should follow. 1, a learner should be able to identify a parent name. Now, when you are identifying a parent name, we usually say it's a longest chain of carbon atoms. 2, a learner must be able to identify the homologous series or the functional group that the compound belongs to, which it will give the suffix of the name. 3, a learner has to be able to identify the substituent or the branch, which gives the prefix of the name. Now, we should always ensure that all carbons are surrounded by 4 bonds, because a carbon, for it to be filled in the outer orbital, there must be 4 orbitals that are filled. It includes a hydrogen bond. It includes bonds with your halogen. It includes bonds with your oxygen. Now, a learner should always ensure that all of that is checked. And obviously, for your oxygen, there must be 2 bonds around it. And for your hydrogen and all halogens, there is 1 bond that is attached to that. Now, we then go and talk about isomers. There are 3 types of isomers that a learner must know. 1, a learner must be able to identify what is a structural isomer, because a structural isomer is an overall concept of isomerism. Now, if you know the structural isomer, you are able to differentiate the 3 other isomers that we get to talk about. Isomer number 1 that we talk about, it is a chain isomer. Now, a learner, when you are able to identify a structural isomer, that it is molecules of the same molecular formula but different structure. Now, when we talk about a chain isomer, you know we talk of different chain. When you talk of the positional isomer, then you will know that you are differentiating it with a different position. Now, you need to know that when we talk about a positional isomer, it can be a different position of a functional group, or different position of a side chain, or a substituent. And lastly, we talk of a functional isomer. And when we talk of functional isomers, I usually say to my learners that there are 2 sets of functional isomer. 1, when you look at your carboxylic acid and esters, a carboxylic acid with 5 carbons and an ester that has got 5 carbons, those are functional isomers, because if you were to look at an ester and a carboxylic acid, both of them, they have got same general formula. So they would have same molecular formula, but the type of the functional group will be different. Another set of functional isomers will be between your aldehyde and your ketone. If you look at a ketone of 4 carbons and you look at an aldehyde that has got a longest chain of 4 carbons, those would have the same general formula. Carboxylic acid and your aldehyde and your ketone have got the same general formula. So a chain of 4 carbons in each, it simply means their molecular formula would be the same, but the functional group is different. So there are 2 pairs of functional isomers that you look at: your aldehyde and ketone, your carboxylic acid and esters. Now, whenever we are representing a molecular, your molecules, 1, a learner must be able to write a molecular formula of a substance. You look at your propane. Your propane, its molecular formula would be C3H8. A learner should also be able to write a structural formula of a compound. And when you are writing a structural formula of a compound, we say all bonds that hold atoms together must be visible or must be presented. And lastly, a learner should be able to draw what we say it is a condensed structural formula. That's when a learner does not show all bonds. Now, these are 3 formulas that we would represent our molecules with: a molecular formula, a condensed structural formula, and lastly, a structural formula. And when we are awarding marks for the structural formula, for bonds that are not visible, or for bonds that are being omitted, that simply means the structure of that compound is wrong. Now, we go to the second question, which is question 3 on organic chemistry. Question 3 looks at the physical properties. Now, if we talk about physical properties, there are 3 physical properties that we look at. Your physical property number 1, it is a boiling point. Physical property number 2 is your melting point. And physical property number 3, it is the vapor pressure. All these physical properties of your organic compounds, they depend on the strength of the intermolecular forces. If the intermolecular forces are strong, the boiling point will be higher, the vapor pressure will be lower, and the melting point will be higher. And if the strength of the intermolecular forces is decreasing or it is low, it simply means the boiling point will be lower, the melting point will be lower, but the vapor pressure would be high. Now, you need to have this understanding that for molecules that have got a stronger intermolecular forces, their boiling point and melting point will be high, but the vapor pressure would be low. And for any molecule that has got weaker intermolecular forces, the boiling point and the melting point will be lower, but the vapor pressure would be higher. And when we talk about these properties, we will talk about 3 variables. This question comes as an investigative question. We talk about the 3 variables when we look at investigative questions that are of investigation. Your variable number 1 is your independent variable, your dependent variable, and your controlled variable. And obviously at this point, your independent variable with what has been changed. Your dependent variable will always be these physical properties. So if they are trying to check the melting point of organic molecules, then it simply means that dependent variable is your boiling point. If it's a melting point, it's going to be a melting point or vapor pressure. So your dependent variables will always be these 3: melting point, boiling point, and the vapor pressure. And obviously, when we then look at the independent variable, we will look at the type of the intermolecular forces. Molecules that depend to different homologous series would have different types of intermolecular forces. All your hydrocarbons, by hydrocarbons we mean your alkanes, your alkenes, your alkynes, all of them, they have got one type of intermolecular forces, which is your London forces, which are known to be the weakest intermolecular forces. Your aldehyde, your ketone, your ester, your haloalkanes, all of them, in addition to London forces, they have got dipole-dipole intermolecular forces, which are known to be stronger than the London forces. And lastly, you look at your alcohol and your carboxylic acid. Your alcohol and carboxylic acid, they have got a hydrogen bond, which is known to be the strongest intermolecular force. Now, it is quite easy when you are looking at compounds that belong to different homologous series, because you know what has been changed. It is the type of intermolecular force. So that becomes your independent variable. But when you look at molecules that belongs to the same homologous series, it can be that the difference, it is the chain length or it is the branching of the compound. If it is a chain length, what has been changed? It's a chain length of your compounds. When we talk about molecules that belong to the same homologous series and they are changing in chain length, we are looking at molecules that of alkane. You have got your methane, your ethane, your propane. As you move from methane to your propane, there's an increase in chain length. If you look at the branching of your compounds, we are looking at molecules like your pentane, your 2-methyl propane. You look at those 2 compounds, they are of the same homologous series, same number of carbons. But what has been changed, it is the degree of branching. the intermolecular forces would differ. Now, we usually say for the chain length and the surface area, the responsible intermolecular force for the change would be the London forces. If the chain length or the surface area is increasing, the strength of the London forces also increases. Now, when you are answering questions, there are 3 steps that you need to follow. Your step number 1, you need to be able to identify the difference in structure. 1, your difference in structure can be in terms of the chain length, it can be in terms of the branching of a compound, it can be in terms of the functional group. So if you are looking at the chain length, you would say the one that has got a longer chain length, it has got stronger intermolecular forces. The one that has got a shorter chain length, it has got weaker intermolecular forces. You look at the degree of branching, the less branched compound, it has got stronger intermolecular forces. More branched compound, it has got weaker intermolecular forces. And obviously, when you look at the functional group, you look at the different types of intermolecular forces. You know, rearranging them, your London forces are the weakest, dipole-dipole intermolecular forces, and your hydrogen bond being the strongest intermolecular forces. Your step number 2, you need to state the effect of those intermolecular forces. Now, you know which one has the strongest intermolecular force and which one has got a weakest intermolecular force. So you need to look at the effect of this factor on their intermolecular forces. And lastly, you need to look at how will the energy be. Now we talk about the energy that is needed to overcome intermolecular forces. The problem with learners is that they do not talk about an energy that is needed to overcome intermolecular forces, but they talk about energy that is needed to break bonds. Remember, we don't talk about breaking of bonds, but we talk about overcoming the intermolecular forces that are existing between the molecules of these organic compounds. So we then have got the third question, which is organic reactions. Now, there are different reactions that we look at. Because this is an overview, we are just going to go above the reactions that we have. Reaction number 1 that we are looking at, it is substitution. There are 2 substitutions that we look at, your halogenation and your hydrolysis. Now, if you look at your halogenation, that's when an alkane is reacting with a halogen. There are reaction conditions. Reaction condition for all your substitution, it is mild heat. Now, halogenation, it's mild heat, it's reaction condition, and as a product, you'll get your haloalkane and your hydrogen halide. Reaction number 2 under substitution, it is your hydrolysis, where you are reacting a haloalkane and the base. And obviously, reaction condition, that base, it is a strong base, but it's diluted. And the heat there, it has to be a mild heat. As a product, you get an alcohol and your halide salt. And lastly, you look at your haloalkane reacting with water. So the condition is that you are adding water into that haloalkane, and heat has to be a mild heat. You get alcohol as a product and your hydrogen halide. You look at your reaction number 2, which has got different types of it. That is your addition reaction. Type 1 of addition reaction, it is hydration, where an alkene reacts with water. Conditions there, it's a strong concentrated acid, which is a sulfuric acid. You get one product, which is an alcohol. Reaction number 2 on addition, it is your hydrogenation. An alkene is reacting with hydrogen. And reaction conditions that you get there, it is a catalyst that is used, either a platinum, your palladium, or your nickel. And you get as a product an alkane. And reaction number 3 on addition, it is your halogenation. You are reacting an alkene and a halogen. Now you need to remember, when we talk about the halogen that is reacting with that alkene, a halogen is a diatomic molecule. You look at a halogen yako, that is a chlorine, it will be Cl2. Now when you are reacting an alkene with Cl2, you will get a haloalkane that has got 2 substituents of halogen. And obviously, reaction conditions, it should be room temperature and pressure, but there is no catalyst that is needed. You get as a product a haloalkane. And reaction number 4, which is the last one on addition reaction, you are reacting an alkene with your hydrogen halide. And reaction conditions, no water. As a product, you get your haloalkane. Now, the difference between your halogenation and your hydrohalogenation in this is that your halogenation in addition will have 2 sides of a halogen. It would be either 1,2 dibromo-propane, because you were substituting or you were adding E-propene to a bromine. If you are looking at your hydrohalogenation, there is going to be 1 substituent of halogen, because you are reacting an alkene with hydrogen halide. So there's going to be a hydrogen and there is going to be a halogen that is attached. Now there's a rule, especially for your hydration and your hydrohalogenation. The rule is, for you to get the major compound, is that your hydrogen will go to a carbon that has got more hydrogen. So which means your OH in water or your halogen in hydrogen halide will go to a carbon that has got least number of hydrogens. Now we look at the third reaction, which is elimination. Your elimination type number 1, it is cracking. In cracking, we are breaking a huge compound of an alkane. You get as a product the alkane and your alkene. And obviously, that has to take place under high temperature and pressure. Your reaction number 2 in elimination is high dehydrohalogenation. In dehydrohalogenation, you are reacting a haloalkane and a strong concentrated base. You are having reaction conditions, which is a strong heat. You get as a product an alkene, your salt, and water. Reaction number 3 is dehydration, where you have got your alcohol. You are eliminating water from there, making use of a strong concentrated acid, your sulfuric acid, and strong heat. When you look at your dehydrohalogenation, you would see that dehydrohalogenation is the only reaction that would have 3 products. The reason behind that, when we are removing or when we are eliminating that hydrogen halide is an acid. Now it is removed. We know that when we are making use of that base, strong concentrated base, as much as it is used as a catalyst, but it will still be there at the end of the reaction. Now you've got your acid, which is your hydrogen halide that you have removed. You have got that base, which is there. The acid and base, they are reactive towards each other. So they would react, hence we are having a product that is salt and water, because we know that whenever we are reacting an acid and a base, we always get salt and water. Hence, that elimination of dehydrohalogenation, we get alkene, we get salt, we get water. Now, there is rate of reactions. It's a topic that was covered in grade 11. A bit of it was covered in grade 11. In grade 11, you have learned 2 types of reaction: an exothermic reaction and an endothermic reaction. You should be able to differentiate an exothermic reaction from an endothermic reaction. And obviously, when you are differentiating the 2 reactions, you are making use of heat of reaction. Now in grade 11, you were taught of two concepts, the activation energy and the activated complex. When you are unpacking the issue of rates of reaction, you should have into consideration that you understand your activation energy and your activated complex. And part of your grade 11, we talked about how the addition of catalyst will affect the rate of reaction. And you know that you talk about a catalyst as a substance, you should know what is a catalyst, and you should know what is the mechanism of a catalyst. That a catalyst, it increases the rate of reaction by lowering the total activation energy. But when you talk about a catalyst as a substance, you talk about it as a substance that increases the rate of reaction without itself undergoing the rate of reaction. And this graph you are familiar with, because that's the graph that you looked at in grade 11, where the dotted line, it is when catalyst has been added, and you can see at that particular point in time that the activation energy has lowered in comparison with that activation energy when there was no catalyst that was added. So factor number one, when we look at factors that affect the rate of reaction, we look at the addition of catalyst. Your catalyst, it is there to lower the activation energy, but while lowering the activation energy, it speeds up the rate of reaction. Now, there are different factors that we look at in terms of a rate of reaction. Factor number one, it is nature of reactants. Factor number two, it is your catalyst. Factor number three, it is the surface area. Factor number four, it is temperature. Factor number five, it is catalyst. Now you need to know, when you are looking at your concentration, the higher the concentration, the faster the rate of reaction. When you look at the surface area, if surface area has been increased, the rate of reaction increases. Three, when you look at the temperature, when temperature is increased, the kinetic energy of particles increases. If the kinetic energy of particles has been increased, the rate of reaction also increase. Now, whenever there's an addition of a catalyst, there is always going to be an increase. If that catalyst is a positive catalyst, there's always going to be an increase in the rate of reaction. But that catalyst itself, it does not undergo any permanent change. Now, we talk of calculations of a rate of reaction. There are two things that we look at. Number one, we look at your products. When you look at a rate of reaction in terms of product, you look at a rate in terms of a concentration. Rate would be equal to a positive change in concentration over your change in time, or your positive change in your positive change in mass over your change in time, or your positive change in volume over your change in time, or your positive change in number of moles divided by your change in time. And if you look at your rate of reaction in terms of reactants, in terms of your concentration, it would be negative change in concentration over your change in time, your negative change in mass over your change in time, your negative change in volume over your change in time, or your negative change in number of moles over your change in time. Units are very important. Your example, if you are looking at your rate in terms of volume, units would be decimeter cubed per second. And if you look in terms of mass, the units would be grams per second. And if you look in terms of moles, it would be moles per second. Now you need to be able to differentiate if the graph that you are looking at as you are calculating the rate of reaction, is it the data of products or it is a data of reactants. If it is that of products, remember that your change is always, your rate is always positive, so it has to be change in concentration over your change in time. But if you look in terms of reactants, remember when you start a reaction, you start a reaction with more reactants. And as you are using up your reactants, they will start to decrease. Now, hence we talk about your negative change in concentration over your change in time. Now, we make use of your collision theory when we talk about these factors that affect the rate of reaction. Your factor number one that we look in terms of Maxwell-Boltzmann, it is the temperature. You look at an effect of a temperature. One, we know that when temperature is increased, the average kinetic energy of particles increase. And if that is the case, there is going to be more particles that have got enough kinetic energy, which results to more effective collisions per unit time. That causes the rate of reaction to increase. You should be able to explain that using your collision theory, and you should be able to explain that using the distribution curve. Number two, the factor that we look at in terms of Maxwell-Boltzmann and using collision theory is the factor of catalyst. Catalyst, we know that it provides a lower path of a lower activation energy. Now, if it lowers the activation energy, we can see that as it lowers the activation energy, there is going to be more particles that have got sufficient kinetic energy. If there are more particles with sufficient kinetic energy, there is going to be more effective collisions per unit time, and therefore the rate of reaction also increase. Now, the last factor that we look at in terms of collision theory, it is that one of concentration. When concentration is increased, there is going to be more particles per unit volume. If there are more particles per unit volume, there is going to be more particles that will have correct orientation, or there's going to be more collisions per unit time. If there is more collisions per unit time, it means there is more effective collisions that are taking place per unit time, and the rate of reaction there is also increasing. Now, you need to know that these three can be explained using the Maxwell-Boltzmann distribution curve. But with collision theory, you can always explain the issue of surface area. That when surface area is increased, there is going to be an increase in the state of division. So more particles per unit volume are exposed. If more particles per unit volume are exposed, it simply means there is going to be more particles will have correct orientation, which leads to more collisions per unit time. And that will lead to more effective collisions per unit time. So that increases the rate of reaction. Okay, learners, that is it for this part of the lesson. Please join us for the next part, which is a link to the overview of paper 2.